Good morning to Mixed Signal Lecture, first one in 2011. I wish you a happy new year, good success in your studies. Good to have you here. I hope you feel motivated for the new year, not only for Mixed Signal, but for all your duties in electronics. Today we really start with the A to D converters. Last year we started slowly with this dual slope A to D converter. Today we really go into the details of other A to D converter architectures. Before we start, let's look at a very basic model of an A to D converter, which is very useful in understanding how A to Ds work in detail. However, we will see that this model also has some impairments. It's somehow over-idealized, and you have to be careful when to use it and when not. So, you know, the goal of an A to D converter is to take an input voltage, V in, and to convert it into a binary word. And a very basic model is to say, we take this input voltage and we add a quantization error EF to the input voltage. This is the quantization error. And this gives us the digital output word B out. Very basic linear model. And if I say linear model, then you can see immediately the problem of this, because if we take a look at the converter characteristics, which is this step function, then we see, of course, this is not a linear device. So the linear model is somehow over-idealized because it assumes that we add a quantization error to the input signal that is decorrelated from the input signal itself. So we assume a decorrelated quantization error the assumption is that the quantization error is decorrelated. Not correlated. This is not true, because if we say, for instance, we have this input signal, then the quantization error is exactly this one. Or if we say this is our input signal, then the quantization error is exactly this one. So for each input voltage we have a given quantization error. However, if we assume that the input signal changes very fast, and the change is also quite large, then we jump around on this step function considerably, and we get lots of different quantization errors, and at the end it seems to be a random quantization error which is not correlated to the signal. So we can say the input signal must change fast enough and strong enough. And this is often fulfilled very good if you have a real input signal which is also somehow random, so which is not a steady state or periodic signal, but if you have something that changes a lot, then you have fulfilled this assumption. And then if you can fulfill this, then you can say it is a very simple and useful model. And useful for, especially for analyzing A to D converter architectures. However, you have to be careful, because here it looks as we have only a basic adder. But look what we really add. We have here a voltage. Here we have a binary output word. So you have to be aware that this is only a model for a full A to D converter which does the translation from a voltage into a binary output word. And if you have DC signals, you cannot use this. If you have sinusoidal signals, you also have to be careful whether these two assumptions or requirements are fulfilled or not. But we will see in the in the field of pipeline A to Ds, we will use this a lot. Okay. Last year I ended the lecture with the question, how can we convert a certain voltage just by asking questions that are answered by yes or no. So let's assume we have here our voltage range in between minus 1/2 of a reference voltage and plus 1/2 of a reference voltage, and let's assume we have an input signal given here by this red line. So if you can ask me questions, what would you ask to approach at the value of this input voltage? So what would probably the first question be? Pardon me? Yes. So the first question is about the sign. So is it greater or larger than 0? So the question is it positive or negative? And I will answer, well, it is negative. It is less than 0. Okay? So then we know that the voltage is not up here, not here, but it is somewhere in this range, in between 0 and the max negative value. So what could be the next question? Exactly. So we have this region between here, this 0, and the most negative value, and we subdivide this interval again in 2 intervals. So we say, okay, we can divide it here, and then we could ask, is it in the upper or lower subinterval? And the answer would be, it is in the upper one. And we can continue like this. Wait. Okay. I lost the slide. So we continue here. The next step is to say, okay. Yeah, I lost it. We know now it is in this subinterval, and we divide this again in 2 parts. And the answer is, well, it is again in the upper one. So we know then that it is in this subinterval. Well, we have to assign the answers of these questions to bits in the output word. So we can say, okay, the first one was that we are in the lower subinterval, so we are less than 0. So we assign this as 0. Here we say we are above this threshold, so we assign this 1. Here we are again above the threshold, so we assign this also a 1. And now it becomes a little bit difficult because of the thickness of this pen, but we can say, okay, we subdivide this interval again, maybe like this. And here we can say now the input voltage is below the new threshold, so we have here a 0. Interesting is that if we have the lowest possible value, so if we are below all thresholds, if we are somewhere here, then all the output bits are 0. If I have a very, very high value, then I'm always above the thresholds, and this means that all the output bits are 1. If you think back to the digital codes that we have discussed last year, then which one is probably representing this converter? The lowest value, also it is negative, is all 0, and the highest value, which is positive, is all 1. This is what we called the offset coded representation of this. And offset means that the 0 value here is not all 0, but has a certain finite value, which is which is here 1 and all 0. So this is the offset that we have here. This converter is called a successive approximation ADC. It is called successive approximation because it performs this binary search technique and approaches at the result step by step. So we do one step, then we have a very coarse quantization. After the first step, we know only the sign. After the second step, we know a little bit more than the sign, but we still have a very coarse representation of the input signal. And with each step, we gain one more bit and become more and more accurate. So, to review this algorithm, I want to go through this flowchart. We start the conversion by sampling the input signal. So we say we have a sample of the input signal V in, and we have an internal signal. Here it is called VDA. We will see on the next slide why. We have an internal threshold signal which is set to 0. And then we ask the question, is the input signal larger than this threshold? And if you look at this slide, then you can see the threshold is set to 0 because in the first step we check for the sign. So if the input signal is larger than the threshold, then we set the respective bit to 1. We increment the loop counter and we add a value here, which is Vref over 2 to the power of I to this threshold signal. Or if the input signal was smaller than the threshold, then we set the respective bit to 0, like we did it here, and we subtract Vref over 2 to the power of I from this internal voltage. So exactly as we did it here. We saw, of course, here we are negative. This was the first threshold. Then we reduce it and come to this value. We check it against the input signal. Then we see, okay, it is now larger than the internal threshold, and hence we add a voltage. So what happens here is indeed something like this. We start with this value, we subtract something, then we add it, and so on. And what you can see, the more steps that we perform, the more converges this internal voltage to the sample of the input voltage. So we have an internal voltage, VDA, and the more steps we have, the more equal is the VDA to the input signal, V in. And after a certain number of steps, which corresponds to the number of bits of this A to D converter, we stop the algorithm and then we are finished. Let's look at the block diagram that implements this. We said we sample the input signal in the first step, and hence we have here a sample and hold block, and this sample and hold is clocked with a clock frequency f clock, which corresponds to F sample. Okay, so perhaps it's better to write here F sample. You can see here on the right hand side we have a D to A converter. And this D to A converter generates the voltage VDA, which is the internal signal that is always compared to the sampled input signal. You can now also understand why we call this VDA, because it is controlled by a D to A converter. So at the beginning we have here the 0, we compare it to the input signal by subtracting the two signals and feeding them to a comparator. So here we check whether the input signal is larger or less than the internal signal. And depending on this, we either increment the output voltage of the DAC or we decrement the output voltage of the DAC. Then we have a new DAC voltage. We compare it again against the input signal, and according to the result, we set or reset the bit of this DAC. So the important or the interesting thing is that the basic building block of this successive approximation ADC is a DAC. So the core component is a digital to analog converter. So the ADC is mainly a DAC and a comparator. Of course, also some control logic that organizes this conversion flow that says, okay, I evaluate the result of the converter of the comparator, and then I set or reset the respective bit. But in principle, it is mainly a DAC, and the conversion principle is, as we said, this is a binary search technique. With the goal, make DAC voltage equal to the input voltage. If we sample here the input with a certain sampling frequency, then for each period of this sampling clock, we have to perform n cycles. So everything in here, the logic and the DAC, works with a higher frequency, which is n times f sample. So internally, the speed is much higher than the sampling frequency. And if you think back to the overview slide that we had last time, and we said there is a successive approximation converter, which is a device performing a binary search technique, then you understand why this converter is for medium frequencies and not for very high frequencies. Because for each analog sample, we have to perform n cycles internally. And then we take the next analog samples and we have another n cycles in here, where n is the number of bits of this converter. Or if we use a more advanced device with a redundant algorithm, then it can be even more. Also interesting to note is that the difference between the internal voltage and the sampled input signal is exactly the quantization error. This is good to note if we go into architectural details today. Okay. Is there questions so far? Basic principle is clear or not? Okay. In order to go towards the implementation of such a device, we use a modified SAR algorithm, which is basically intended for unsigned signals. You can extend this to signed signals, but here I will explain it for unsigned signals. The first step again is to sample the input voltage. Then we generate an auxiliary signal which is called Vx, and this Vx is simply minus the sampled input voltage. So we say Vx is minus Vin. Then we first increment the Vx. Okay, this is different to what we did so far. So far we checked first against the internally generated voltage. Now we first increment the internal signal. And then we do not check it against internal voltage, but we always check it against 0. Well, if the internal signal is larger than 0, then obviously this increment was too large, so we undo the increment. So here we increment, and here we undo the increment. And we set the respective bit to 0. However, if we are still less than 0, then the increment was not too much, so we can keep it, and we set the respective bit to 1 here and go for the next cycle. And in the next cycle, again, we increment the Vx now by a smaller increment. We check for the sign. If the value that should be negative is now positive, then the increment was too large. We undo it and set the respective bit to 0. If it is still negative, then we keep this increment and we set the respective bit to 1. What do you think about this function? Vx larger than 0. Who attended also an analog lecture? So if you build a comparator which compares always against the same reference, then this is considerably easier than building a comparator that compares against a variable signal. This is due to the signal levels that your comparator has to fulfill. If you compare always against the 0, then you have a constant reference, and you can design the signal, the comparator, especially for this case, and not for a wide variability of the input common mode. So, hence, for implementation, this is much easier, and we will see that this one fits also very well to a SAR architecture that I will describe now. Before we do this, let me write down some information here. So this is also binary search technique. We compare against 0. And this is for sure an implementation advantage. And this one is especially suitable for a converter architecture that is called charge redistribution converter. let's look at this algorithm for an example. Let's say we start here with this value. So we sample this as an example. So we have here a sample phase. And the first step was to invert this sampled value. So we take this value and simply invert it. And then we end up with this value. Okay. Then we have to check, is this larger or smaller than 0? And of course we can see it is less than 0. So we add vref over 4 to this result. No, we add vref over 2. And we come up here and have this value. So here we can see we are still less than 0. So let me just a moment. Yeah, we are still less than 0. Hence we go for this branch. So we do not undo this increment, we keep it, and we set the bit to 1. So we set this to 1, and now we increment again, however by half the value, and you can see now we cross the 0 line and become positive. So now we are positive, so we run into the other branch and we have to say, well, as we went positive, this is too large. So we set this here to 0 and we undo this increment. So we go back here to the original value. This is what you can see here. If we are larger than 0, then we subtract the same thing that we have added before and end up with the old value and have the 0. Yes? You missed the step from here to here. Okay. So this is the original value. Okay? Then we reverse it. Then we add this increment. Yes. So wait, we can put numbers here. So we say this is the step 1. Then we invert it. Then we increment it. Okay? This is what we see here. This is the 1. Then we invert it. This is the 2. Then we increment it. This is the 3. Sorry, I didn't get it. Okay, no, first we increment it without comparing, then we compare, and depending on the result, we keep it or we undo it. Then here we check. Okay, we increment again. Here we see that the increment was too large because it brings us above the 0. Hence, we undo it here, and we add another increment here. And here we can see we are below the 0, so we can keep it and add another increment and so on and so on. And what you see here is different from the previous algorithm is that we do not converge against the input signal, but the more we continue to do this algorithm, we converge towards the 0. So this signal, which was called Vx, gets more and more to the 0. So perhaps it converges to the 0, okay? Say convergence to 0. Okay? So the question is, how can we now implement this? And the principal circuit is shown here. You can see this is a switch capacitor circuit, so we can use all our knowledge that we have gained during this switch capacitor chapter. Let's go through this circuit in detail because we have several phases here, and the first phase is shown on this slide, and it is the so-called tracking phase. What do we have? Well, first we have here a feedback switch around an amp. And this feedback switch means that this means that we have here an op-amp configuration where the op-amp works in linear mode of operation. So this here is simply a voltage follower with a 0 input signal. So here we have the output signal V out equal to 0. And we use this device because it generates a virtual ground signal here. So this is virtually equal to this analog ground that we have here. We connect via these switches all these caps to the input signal. So up here at this plate we have the virtual ground. At the other plate of the caps we have the input signal. So the voltage across all caps is the same. They're all in parallel. And it is equal to minus V in. Okay? The total amount of capacitance here is C total equal to 2 to the power of n, normally minus 1 if we have such a binary weighted network, but you can see here we have the LSB kept twice, so we have 2 to the power of n times C as a total cap, and we have this in a binary weighted form. So we have a binary weighted capacitor network. And of course, if we have a total capacitance, we have a voltage drop across all caps that is known, then we can also compute the total charge. And this total charge is Q total equal to C total times the voltage, which is minus V in. Or in our example here, we have 2 to the power of n times C, which is 32 C times V in. Okay, this is the starting point of the conversion. We sample the input signal on all these capacitors. The voltage is inverted, seen as a voltage drop across these caps. All caps lie in parallel, the output signal is 0, and that's it. So we are prepared for the conversion here. What is the next step? The next step is that we first open this switch here. So this is the first step. What is the result of this? What about this block? What is different from the previous slide? I mention this all the time because it is important and gives often rise to errors in the analysis of a circuit. There is no feedback. And what does it mean if there is no feedback? Yes, this op-amp does not work in linear mode of operation. However, this becomes now a comparator. And the output signal is V out, depending on the input differential voltage. So this is our input differential voltage Vd. And this Vd is equal to minus the voltage on this node, so minus the Vx. And this is Vsat if the Vx is less than 0, or it is minus Vsat if the Vx is larger than 0. So it works as a comparator. We can use this to compare against 0. The second step is that we toggle all these switches This is the second step. And finally, the third step is to switch this switch and connect this rail, which is currently connected to nothing, to the reference voltage. So this is now Vref. What happens to the charge on the capacitors? So on the last slide we had the total charge Q total, which was given by the input voltage and the total capacitance. What happens to this charge? It is what? Sorry. Yes, but can the charge leave these capacitors? So they were all in parallel? Yes. The total charge is not changed. This is very important. And the total charge is not changed, you're perfectly right here, because we have opened the switch, so no charge can escape here. There is this high impedance input into the op-amp, no charge can escape here. So there is the possibility that you mentioned that charge is transferred from one cap to the other, but charge is not leaving the array. And there is also no charge transfer currently between the caps, because they are still all in parallel. They are connected to this node X, and they see the analog ground on all other nodes. So the total charge on the caps cannot change. And hence, the voltage drop, which was here, this minus V in, is still there. So here, across these caps, we have a minus V in. And this means that the potential of this node X here, let me take green color, the potential of this node which we call Vx this Vx is equal to the voltage drop across the cap here. So we have, as already stated here, Vx equal to minus Vin. Good. Next step is that we keep everything as it is. However, we now toggle the very first switch and connect it from the analog ground here to this reference voltage. This is what we have here. Okay. Now, what is the voltage drop across the caps? Still, we have here all caps connected between X and analog ground. So here we have this voltage equal to Vx. However, we have one cap here. This one is connected between the node X and the reference node. So we have here Vx minus Vref. And now we can compute the total charge and say, okay, the total charge is Q total, is the sum of the charge on all of these capacitors. And this one is 16C times Vx minus Vref plus 8C Vx plus 4C Vx and so on, plus 2C Vx plus C Vx plus C Vx. So at the end we have here 16 C Vx, we have here another 8, 12, 14, 15, 16 Vx. So in total we have 32 C Vx minus 16 C Vref. And we know that this has to be equal to the total charge that we had 2 slides before, because the total charge has not changed in between. So this is equal to what we had here, this 32C Vin. So we can set this equal to 32 was minus 32 C Vin. And now we can solve for the Vx and say, okay, the Vx is equal to minus Vin plus 16 over 32, so plus 1 over 2 Vref. And this is what happened exactly in this modified SAR algorithm. Let me go back. One step was to say we add Vref over 2, and then we check for the sign. Okay? This is what we have done now. We toggle this switch here. By doing this, we add Vref over 2. Then we use this comparator here. We use this comparator. And depending on the result, whether we cross the 0 or not, we put the switch back or we keep it as it is. And now it comes into the play exactly what you said, that now, although the total charge is the same, we shift it between the caps. And this is the reason why we call this a charge redistribution architecture, because we move the charge from one cap to the other one, but the overall charge remains the same. Okay, so what we did here is to increment internal voltage by Vref over 2 here, and then check for the sign. And then we can do this for the next switch. We can now then continue with this one. Just a moment. We can continue with this one and search for the next bit. And by doing this, we say, okay, we have then, depending on the decision that we had here, we had a total charge which is minus 32 CV in. And this has to be equal to 16C Vx minus B1 Vref. By having this B1 here, we include the result from the previous step, and then plus 8C Vx minus Vref. This is for the second step. And then we have all the remaining caps, which is 8C Vx. And if we solve this for Vx, we have the minus V in plus B1 1 over 2 Vref. This was what we had from the first step. And now plus 1 over 4 Vref. So this is the next step, and here we have to check again for the sign. And so on and so on. The increment is always reduced. We add it, we increment it by toggling the switch, we check the sign. Depending on the result, we keep the switch position or we switch it back. Okay, there was a question. Can you repeat it in a little bit louder, please? Oh, there is no charge cancelled. Why do you think it is cancelled? Why this transferred from one to the other? Yeah, it is transferred from one to the other because there is a different voltage drop. If you look on this condition here, the voltage across all caps is the same. Okay, so the charge on this cap, on each cap, is given by C times this input voltage. Then, if we go to this phase and if we toggle the switch here, then you see that the voltage drop here is now Vx minus Vref, because we connect here this bottom node to the reference voltage. And as the voltage across the cap changes, also the charge changes. However, this charge is not dissipated to ground or to somewhere, but the change of charge on this cap is placed on the others. Because the top node is completely isolated. So the question is, why can't the charge come from the Vref to the capacitors? Well, in a capacitor, if you place charge on one side, you also have to take it from the other side. And this common node for all these caps is isolated from the environment. So no charge can come out or go to this node. So any charge on one cap has to be placed on the others because it cannot leave this. And if we toggle the switch towards Vref, then we rise the bottom of this cap. So you can also imagine this as a kind of charge pumping. Here all the bottom nodes are connected to ground and the caps are charged. And now you push up one because you put the bottom to Vref. And so the charge that is due to this push-up is is placed on the other caps in order to equalize this, and then we end up with the respective Vx potential that is then compared against the zero. But you're right, the essential in understanding this circuit is to note that no charge can escape from this node. And then you can do this total charge analysis as I did it here to compute the result. Okay, other questions on this one? Of course, this binary search principle is not limited to this charge redistribution converter. You can also imagine that you take a resistor string to generate all possible voltages, and you use a binary search technique to search within this resistor string. Or what you can do, as shown on this slide, is to choose a combined approach, that you do a coarse search in a resistor string. And here you have the advantage, as for the DAX, that the resistor string is inherently monotonic. And then for the LSBs, you might use a binary search technique in such a charge redistribution array. So this slide should say only the binary search technique is not limited to the charge redistribution, and if you see other approaches or combined approaches, it's essentially the same idea behind it, and you can build DAX, ADCs on that one. Okay, let's look into more details of our successive approximation converters. And for doing this, please remember what we had at this node. This is the block diagram that we had before. We had the sample and hold. Here we compare the internally generated signal against the sampled input signal. The comparator says larger or smaller, or in this case we can compare against 0, and steers the successive approximation register accordingly in order to increment or decrement the DAC output. And at this node, this was what we had is the quantization error, and the goal was to make this error voltage equal to 0. The goal is to make this error voltage equal to 0. Okay. Let's partition the DAC here and look into the details of this DAC. And then we might end up with an architecture like this. This is more or less, or no, it is exactly the same, only that we look into the DAC. You can see here we have the input voltage here, and the DAC is now separated in several sub-DACs, and you can see that these sub-DACs are all the same. Same reference voltage, same DAC. So we have here a thermometer coding. And what was the main disadvantage of thermometer coding? Well, it is for sure the effort, because for each step we need another element. However, the advantage was it is strictly monotonic, and we can here compute the remainder, which is this error here, the quantization error. This is E equal to V in minus B1 Vref minus B2 Vref minus B3 Vref and so on, minus B4 Vref. for a binary search technique, and from an effort perspective, it is advantageous to use not equal DEX, but to use binary weighted DEX. So this means we have one DEC that we use for the first iteration cycle. We have here -1/2 times Vref. For the next cycle, we use 1/4 Vref as the reference voltage, then 1/8 Vref, 1/16 Vref. And in each cycle, we choose one bit here. So this is a binary coding. So this is desirable to reduce the number of subdecks. So we have here a reduced number of subdecks. And we can again compute the remainder. And this is E equal to V in minus B1 Vref minus B2. Sorry, I forgot the scaling factor. This is minus B1 1/2 Vref minus B2 1/4 Vref minus B3 1/8 Vref, and finally minus B4 1/16 Vref. Interesting here is that the error contribution also scales with the weighting factors. So it is good to note here that the MSB deck has the strongest matching requirements, because due to this highest reference voltage here, error contributes the most. And the more you go towards the LSB, the less is the error contribution. So if your task would be to build such a device, what do you think is the main disadvantage that we have here? Look at this. We have 4 different reference voltages. So basically you have to build 4 different decks here. So the question is, can we simplify this somehow? And what we could do is to say, well, we remove the scaled reference voltage and we put a scaling factor here. So we say we scale this down, result down. And let's say we use a constant a equal to 2. Then we have here a to the power of -1. You can get rid of this 4 by saying, okay, I scale the result here by a to the power of -2. So scale this by 1/4. And you can get rid of this 8. And then we have a to the power of -3. And here we have a to the power of -4. Okay, you might say this brings nothing because we just shifted the scaling factor from the reference voltage to the output signal, which is not a big deal. However, what we can continue to modify the circuit. I copy this here. By saying, okay, let's insert additional scaling elements. Let's say, okay, we insert here a to the power of 1. Now the circuit has changed. In order not to change the circuit, we can say, okay, we have here another scaling factor, a to the power of minus 1. So the a and the 1 over a here, they compensate, so now we have changed nothing. And we can do this in each step. We can say here we insert an a square, here we insert an a to the power of minus 2, a to the power of 3, and here a to the power of minus 3, finally a to the power of 4, and a to the power of minus 4. Okay. Let's take the upper one as the reference and now do the modification in the lower one. So we have a minus 1, a 2, a minus 2. Okay. Let's take this one and put it across the sum. Well, the reason why we are allowed to do this is to say, okay, here we have a summing element. We have two inputs. This one is scaled by a, this one is scaled by a, and as this sum operation is a linear one, we can equivalently replace this by saying, okay, we do not scale this input, we do not scale this input, but we scale the result. Okay? This is the same. And this is what we do now in the circuit. So we take this one and put it here. Okay? I have here a to the power of minus 4, but I remove this one and I remove this one. So here we can say this is a scaling element right before a comparator, and the comparator only checks for the sign. So if the signal is a little bit larger or a little bit smaller, this is not relevant for the sign. So we can also remove it here. Good. Then we say we take this a to the power of minus 3 and this a to the power of minus 3 and place it here. Okay? Then we can delete this one, and we have here a to the power of minus 3. We can do it also here. We can shift the a to the power of minus 2. Then we have here a to the power of minus 2. Can delete this one and can delete this one. And finally we can say we put this a to the power of minus 1 here, and we can delete it here and here. Let me remove everything that we have deleted. So we do not have this, and we do not have this. So what remains is this. And here you can see we have a to the power of minus 3 scaled by a to the power of 4. So we can also say we delete this and replace it by a simple a. Here we have a to the power of minus 3 times a to the power of 3. This gives a single a, and we remove this. And the same here, we remove this and have a simple a. And now the circuit looks like this. We have only the scaling factors in the signal chain. So the interesting thing is now we have the same DAX with the same reference voltage, but after each step we scale the signal. So we do the subtraction here, and then we scale the signal up. We do the next step and we scale the signal up. I summarized this on this slide. So you can see that the binary weighting can be also achieved by the same DEX, same reference voltage, but by scaling factors in the signal path. Okay, I'll write this down. By the same DEX, by the same reference voltage, but by scaling up the remainder. So this is scaling factors in the signal path. And this is interesting. Sorry, what we did so far is that we took a signal and that we added or subtracted something which was reduced in each cycle. So we started with 1/2 times the reference voltage, then in the next step we had 1/4 times the reference voltage, and these increments got smaller and smaller. What we have now is that we take the remainder, we do not reduce it, but we scale it up. Okay? So we do a decision with a certain DEC, we take the quantization error of this step, and we bring the quantization error up to the previous level. Let me illustrate this with this algorithm. So you can see here we start exactly in the same way. We sample the input and have an internal voltage which is equal to the input signal. And then we check for the sign. Well, if we are larger than 0, then we decrement the internal signal by Vref/4. Otherwise, we increment the signal by Vref/4. And the new thing that you see here, it is always plus or minus Vref/4. It is not Vref/2 to the power of I, where I is the loop counter. But it's always the same, which is also easy for implementation. And then you get the remainder, you get an error. And this error is now scaled up by a factor of 2. How does this look like? We have here our voltage range. Here we have a 0. And here we go with the steps. Here we have the V. We have here the 1/2 Vref. We have here a minus 1/2 Vref. And then we also have the 1/4. This is 1/4 Vref. Okay. All voltages that are in this range, for these voltages, we are positive. So we can say V larger than 0. Well, for the red voltages, yes. So we set the respective bit to 1. And we have to subtract Vref/4. So we go down by Vref/4. So the red voltages are transferred into this voltage. So this one goes here, this one goes here, and so on. For all voltages that are negative, so for all these green voltages, we say V larger than 0, no, so set the bit to 0 and add Vref/4. So the green voltage bar goes here. So this one goes here, this one goes here, and so on. And then, finally, we say, now double the error, the reminder. So both the new red and the new green bar is now scaled back to the original interval. So they go up here again or down here again. And then we are in the same range and we do exactly the same thing again for the next cycle. So no need to scale down the increment or decrement or do something like this, just by scaling up the reminder and bringing it to the original interval. So we can exercise this also for an example. We can say we start here. Well, now we are larger than 0. So we set this equal to 1 and we decrement it by vref over 4. So we go down here, we decrement it by vref over 4, and this is our reminder, and we double this error voltage and end up here. This is still larger than 0, so we set the respective bit to 1, but now we again decrement it by vref over 4, and we go down here and end up here. So this is our new error voltage, and we double this new error voltage and end up here. This one is negative, so we set a bit to 0. We increment it by vref over 4, get this new error voltage, and we have to double it. Now we are positive again, set it to 1, subtract vref over 4, double it, see that it is negative, and so on and so on. The difference here is that you can see we converge neither to 0 nor to the sample value. The error signal is still high. But this is nothing bad, because it is still high, because we bring it back to the original value in each step. And it simplifies also somehow all the analog components, because the signal remains high and we do not have to cope with very, very small signals here. This is what people call an algorithmic analog to digital converter. Well, it's simply a modified version of the successive approximation converter. It is a variant of this. The idea is the same. The idea is to have a binary search technique to figure out the value of the input voltage by doing this question and answer game and doing this binary search. Okay. Is there a question so far? Let me give you another illustration of this algorithm, which some people call a residue plot, or which is also known as the Robertson diagram. And it is simply a graphical illustration of this algorithm, but an illustration that helps you to understand the problems in a converter and that may help you to understand the operation. Well, we have in this algorithm, this is a copy of the flowchart from the previous slide, we have always the case that we modify the internal voltage, which is first the sampled signal. We modify this in each cycle. We either decrement or increment it by vref over 4. So what you see here is the voltage when we go into a loop cycle, and this is the one when we come out of the respective loop cycle and go into the next one. So we have a V in when we start here, then we do some modifications, and then we get a Vi plus 1, which is the input voltage for the next cycle. So what you see here is the voltage that we use to go in here. What you see here is the voltage that we have at the output of one loop cycle. Then we say, okay, if the voltage is larger than 0, so if we are in this region here, then we compute the new voltage by subtracting Vref over 4 and doubling the result. So if we say the Vi plus 1 is equal to 2 times Vi minus Vref over 4. This is what you have to compute if your voltage is positive. And this equation is equivalent to this line here. This line represents this equation. And this line here represents the equation V. No, let me put it up there. Vi plus 1 is equal to 2 times Vi plus Vref over 4. This one is this. This one is this. Okay? And then it is, if you look at this step here, well, this is only due to the sign. We have to distinguish between positive input voltage or negative input voltage. So we are either on the left or on the right. Good. Then it is useful to have another line. This is the blue one, and the blue one is Vi plus 1 equal to Vi. This is an auxiliary line that helps you to perform this algorithm. So let us start with a voltage, input voltage that is, for instance, here. So this is our V in. We sample this and then we go into the algorithm. Well, we see that it is positive, so we have to go to this branch, and in a graphic way we say, okay, this voltage leads to this reminder. Okay? We are positive, so we have a 1 here, and we have this reminder. And this Vi plus 1, we have to take this value and place it into the second loop cycle. So we have to measure this value and put it here in order to go for the next one. We can do this in a graphical way by saying, okay, if I go here horizontally to the blue line and then down here, then this is exactly the same value. So here, if I go like this, then I have copied this value towards the x-axis. Okay? And then I see this is my new value here. So I go up here, and this is the new one. This was negative, so I have a 0 here. Then I can do the same thing, go towards this line, and up here. I can go here and here. From here I can go here and here. So you can go through this algorithm also in a graphical way. And going for the blue line is simply to copy a value in the y direction into the x direction. Is this clear how this works? Yes, I can explain it again, no problem. let me clean it up. I put you this slide, which does it with real straight lines without any drawing errors into the web, but I prefer to explain it here like this. I can do it again. Let me clean up. Let's start with this value, okay? This is our V. Then we have to compute the new V. So we can compute it by searching the point on this red curve. Because the red curve describes how to come from the old V to the new one. So then this is my new V value. Okay? Then you can take a ruler, can measure this distance. You have a negative value, so you can place this line somehow here. Okay? Just take this one and place it here. You can do this also in a graphical way by saying, well, this is a V in equal to V out curve. So you can go towards this curve. So this should be parallel to the x-axis and can go down here. Okay? Then you know that the distance from here to here is equal than the distance from here to here. Okay? That's the point. And then you take this one as the new value. So you go up here, this is your new value, and then you do the same thing. You go to the blue line, and then you can say, okay, here, this is the new one. And you go from here to here, and so on. So you can use this blue line as an auxiliary line to avoid to measure the value along the y-axis and place it on the x-axis. This is just a simplification, so that then you can draw it immediately like this. Okay. As I usually try to draw straight lines which are not straight at the end, I did this with MATLAB and I put this into your slides here so you have a precise version here. Okay, finally we can place this in a block diagram and look at the components that we have here. We have our input voltage that is sampled by a sample and hold. The sampled and hold version of this voltage is then compared, and depending on the sign we either add or subtract Vref over 4. From the modified version we have to create a doubled value. So we need an amplifier x2. We have to double this, and then we can go to the next iteration cycle. Still the basic components is a comparator, is of course the sample and hold, is something that subtracts here a reference, Vref over 4 or minus Vref over 4, and a circuit that doubles the remainder. And we will see next week that it is very important that the threshold of the comparator is precise, and it is also very important that the gain factor x2 is precise, that it is not 1.9 or 2.1, but it is exactly 2. And therefore, there is, or a good thing to do is to do this amplification with switch capacitor circuits due to all this robustness against component variations that we have discussed. And I placed you an example for an X2 switch capacitor circuit in your slides as an add-on material. and I recommend that you go through this circuit. Well, the basic idea is in this circuit to sample the input voltage, take the charge that you have on your sampling capacitor and store it somewhere. And then sample the input voltage again on the same cap. And at the end, to combine these two charges. So you sample the input voltage, you sample it again, and then you combine the two charges. So the factor of 2 is not by ratio of caps or by ratio of resistors or whatever, but the factor of 2 comes into the play by sampling twice. And hence it is a very precise factor of 2. Because sample, sample again, combine. Then you have the charge 2 times, independent of any variation there. So go through this circuit. It's a very useful one to amplify the remainder by a factor of 2. Next week we will continue with this, and we will start with this block diagram. Because the main drawback that we have in this circuit that we have to sample the voltage and then we have to do n cycles. So we go around here n times. And of course this takes a lot of time because we have to do n times the comparison, we have to do n times the plus minus Vref over 4, n times the x2. And next week I want to discuss with you guys how we can accelerate the circuit to go for a higher sampling frequency. Any idea how we could do this? Okay, think about it. I will come back to this one next week. Wish you a nice week. Thanks for attending and have fun with the tutorials today. Thank you.